Hello everyone, welcome to this talk on a new path to NVMe in Linux. Myself Kanchan and I'm joined by my colleague Anuj. We are from Samsung. Thanks to Sneha for hosting us. It's a pleasure. So here is the outline of the talk. We start by highlighting the growth of something undesired. And that is the semantic gap between the operating system and the OS and the storage interfaces. We explain what NVMe generic device is and how it helps. Then we go about elaborating why and how of connecting this to ioring. To that end, we delve into ioring command and new pass-through path. And in the end, we cover a bit of tooling and look at the scalability data of this path. Starting with something that we all have been seeing, and that's the surge of storage innovations, particularly in NVMe storage. So much so that now NVMe spec from 2.2 onwards had to come up with a new entity called command set to allow grouping cluster of such innovations. We already have two more command sets, GNS and KV, apart from the original NVM set, and more are underway. These new interfaces, they represent the class of optimization that are not automatic in nature. Rather, these require close collaboration with the host. But on the host side, host operating system requires a layer of abstractions to deal with different devices in similar fashion. And while that is good, but that makes fitting new storage interfaces into these layers difficult. And the problem only gets worse if we require the creation of a new user interface, because there's a risk that a short-lived storage feature may create long-term maintenance burden on the operating system. Another related but somewhat different aspect is that IO is no longer classical read and write. We already are seeing various new ways of reading from and writing to the storage. Few examples. With Joan append, host does not dictate where to write, but storage tells where exactly write took place when it completes the write. Copy command, which is a in-device copy facility between a single namespace. It requires multiple destination LPA and one source LPA. We do not have any existing system call which can fit well with that. With KV, things get more radically different as the LBA concept itself vanishes and host needs to speak keys and values. Since all these new commands are hard to turn into operating system call, what we are left with is ioctl driven pass-through interface. But ioctl is really far from all the OS level innovation that have been done for read and write. If you look at the table over here, ioctl is a synchronous call which defies the purpose of using NVMe, that is highly parallel. Read and write also allows using multiple buffers in a single call, while ioctl does not, and that's the vector IO feature. One can amp up the efficiency of read-write further with things like summation polling and completion polling, but that's not possible for ioctl. And just in case you thought things can't get any worse, there is something more. ioctl, or any syscall for that matter, is issued against an object. And in the case of NVMe, that's the block device node /dev NVMe 0 and 1. For a new storage, this block interface itself may not exist, or it may be there but unusable. And ioctl cannot be issued into the thin air. So that gives this availability problem of the block interface. The block device may show zero capacity, it can turn read-only, or maybe mount hidden. And this can happen in a variety of situations. Few examples are Unsupported LBA format, which is what is shown in this diagram, for an NVMe device formatted with 4 KB plus 8 byte LBA format, block device node shows 0 capacity. A GNS drive without joiner pen, it is shown as read only. And a GNS drive with non-power of 2 zone size, the block interface won't come up at all. And same happens for NVMe device with new command sets, other than NVM and GNS, I mean. NVMe generic device is answer to the availability problem that is linked with the NVMe block device. It's a generic device is a char-device node in the form of /dev and g, and one for each namespace. Both block and the char-device node can exist for each namespace, so it is not a substitute but alternate. Block device may or may not come up, but char interface always comes up regardless of the unsupported feature or a new command set. It's available in the mainline kernel since 5.13, and that was last year in June. And the support for anonymous command set, the unknown command set, is planned from 5.20. While the availability problem is addressed by the generic char interface, we wouldn't want to be locked to ioctl for using this interface. So this new path connects the char interface to iuring instead. NVMe driver and the iuring, they collaborate to create this new pass-through, which made its way in 5.19. As we see in the picture, the path is devoid of block and FS abstractions. So application can speak the same language that device does. And every NVMe command can be issued as efficiently as regular read-write. Be it async dispatch, vectored buffer, or submission polling, they all are already up for this, while completion polling is underway. So NVMe pass-through use ioctl, but so did many other components in the kernel. And despite its heavy use, Linux did not have the alternative of async ioctl. iuring command offers what async ioctl, if it had existed, it offers that and much more than that. So we cover that as we move along. But before that, some iuring basics. So it's a scalable asynchronous infrastructure for both storage and network IO. It has already added async variant of various synchronous system calls. And all that is, the cool thing is that all that doesn't require adding new system call. With the existing interface of iuring, it's possible that we add async variant without adding a new system call. And if you look at the user kernel interface of it, the backbone here is a pair of ring buffer, submission queue and completion queue, which is shared between user space and kernel, and that helps in reducing the system call and the need of copying data around. The programming model is it's straightforward. Application get to pick a SQE, fill it up with all the information that is required to prepare the command. It can fill some more to make a batch, and then it can submit the whole batch by calling the system call called iuring enter. And when it wants to do the completion, it can read the CQE from the CQ ring. And some more goodness it comes from the fact that the submission can be offloaded to the kernel, and that means no system call at all. And the completion can also be pulled, and that gives interrupt-free IO. Now, this is an example of how a sync call, in this case, pread, is mapped to iuring SQE and CQE. The right-hand side is the structure of the SQE. The read operation is conveyed by the IO-ring opcode, IO-ring OP read, and that goes into the SQE opcode field and other fields like FD, buffer address, all that are also placed into respective fields of SQE. That's about summation. For completion, pread returns the number of bytes read. And for IO-ring, application can get the same information by reading the result field of the CQE. Now we talk about IO-ring command, which is a facility to enable IO-ring capability for any underlying command. And async happens to be one such capability. The command provider could be one of the kernel component, like a driver or a file system. And the driver and this component, this command provider collaborates with the IO-ring to make it happen. NVMe driver is the first such collaborator, while uBlock driver is the second one, which is scheduled for 5.20 kernel. If we look at how application can use it, it need to specify this new opcode, IO-ring OP uring command, fill the SQE as before. But exciting part is that the ioctl command doesn't have to be use a space pointer. Rather, it can be placed in line into the SQE itself. And that reduces the allocation cost. If the command is 16 byte, we use the regular SQE. And if the command is larger, up to 80 bytes, we can ask IO-ring to set up Big-SQE. For completion 2, there is something new. While one result can come into CQE as before, now we have the option to ask for Big-SQE. And with that, the kernel can return additional result to the application. Now I will hand it over to Anuj for a deep dive into NVMe side and for rest of this talk.
Thank you, Kanchan. So now we will see how do we move from the ioctl based passthrough to the IO-ring based passthrough. Let's begin. So let's first look at the ioctl based passthrough. So here the user requires to allocate and prepare a NVMe passthrough command 64 structure. The structure is shown in the diagram here. So during submission, the kernel will do a copy from user call to copy the passthrough command from user space to kernel, and this is one of the overheads during submission. Similarly, during completion, the NVMe device will return a result back to the host, and this is an extra result apart from the actual status code, and this value needs to be copied back to the user. So this result is a part of the pass-through command structure only, as highlighted here, and the kernel will do a put user call to copy this result back to the user. So again, this is an overhead in this part. Moving forward, so now let's talk about the IO-ring based pass-through. So here the user will prepare a NVMe uring command structure. So the structure is shown in the diagram here. And this structure is similar to the NVMe pass-through command 64 structure that we discussed in the previous slide. But the difference here is that there is no 8-byte result field in this structure. So as you can see here, there is no result field. And that's why this structure is 8 bytes smaller than the NVMe pass-through command 64 structure. The good part about this path is that there is no copy from user overhead and no put user overhead. We achieve this using something called Big-SQE and Big-SQE. And what exactly is that? We will see it in the next few slides. So let's talk about Big-SQE. So Big-SQE is a modified version of the existing IO-ring SQE. It is double the size of a regular SQE. So if you see this diagram, right? So you can imagine Big-SQE has two regular SQEs stacked on top of one another, where the first SQE can be used to store the command specific information, for example, the file descriptor, the ioctl opcode, and the IO-ring opcode, and all of the other information as well. Which means that the second SQE is completely free. Also, another thing to note here is that in a regular SQE, the last 16 bytes is nothing but padding. This means that the last 16 bytes of the first SQE combined with the 64 bytes of the second SQE is completely free. So this gives us 80 bytes of free space in a big SQE. Now we can use this free space to pass the pass-through command, and we will be able to save the allocation cost. At the same time, because the SQE is shared between the user and the kernel, there will be no copy from user overhead in this path. So if the application wants to use the Big-SQE facility, then the application would have to specify the iRing setup SQE128 flag at the time of ring setup. And once the application does that, the command field in the SQE will start pointing to the 80 byte of free space that we just discussed. Okay. So coming to Big-SQE. So Big-SQE is a modified version of the existing IO CQE. It is double the size of a regular CQE. So if you see this diagram here, you can imagine the Big-SQE as two regular CQEs stacked on top of one another. The first CQE can store the user data flags in the IP status value, whereas the second CQE is completely free. So this means that it will provide us 16 bytes of additional space to store the extra result. And we can use it to store the extra NVMe result in the passthrough command case. Now, if an application wants to use the Big-SQE, then it will have to specify the iRing setup CQE32 flag at the time of ring setup. And once the application does that, the Big-SQE field in the CQE will start running the 16 bytes of free space that we just talked about. Awesome. So now let's discuss a program to read from a character device using during pass-through. In this program, we'll be using some of the libviring APIs. So libviring is a IO library, and it provides a simple interface for applications that don't want to deal with the complex IO implementation in the kernel. So the first thing that the application will try to do here is it will try to set the Big-SQE and Big-SQE flags. Then it will make use of a libviring API IO during QNet to initialize the summation and the completion rates. Now the application would want to fetch the SQE from the summation ring, and to do that it will make use of the IO during get SQE API. Once the application has the SQE, it will try to prepare the SQE. So it will set the file descriptor, iouring opcode, which is the iouring op command in this case. It will set the ioctl opcode, and for the pass-through case, it is NVMe uring command I. And as discussed, we don't have to allocate for the command. We can use the inline space available in the Big-SQE. So we will use that and prepare the pass-through command. Now, after all of this, our SQE is prepared. So the application will want to submit this SQE to the kernel, and to do that, it will make use of the iouring submit API. Now, after some time, when the operation is completed, the application would want to fetch the completion queue entry from the completion ring, and it will make use of the iouring wait CQE API to do the same. The application will process the idle status and the NVMe result. So the idle status will be represented by the result field in the CQE, and the NVMe result will be represented by the Big-SQE field in the CQE. Now, once the application has processed the result, it would want to notify the kernel that it has consumed the completion queue entry, and to do that, it would use a iouring CQE scene API. And with this, we are done. So all the libviring APIs that we discuss about, the support for that is available upstream, so you can just go about directly using that. So coming to vectored commands, during pass-through supports vectored command. So what do we mean by vectored command? Vector command enables us using multiple buffers in a single command. So the user would require to specify the NVMe using command iowk opcode, and it will also have to prepare a step iowk array. So each iowk will contain the address of the buffer and the length of the buffer, and it will put all the iowk entries in an array. Now the address field of the enumerating command will point to the starting address of this array, and the data line field of the enumerating command will point to the number of entries in this iowk array. And once the command is prepared, you can submit this command to the kernel. So now let's talk about the tools that we can use to run the test workloads on this new path. And let's actually talk about how this new path scales with the increasing queue depth. So coming to tools, so if you want to run a test workload on this new path, you can use F5, and there are two ways to go about it. You can either use the iuring command engine or the XMME engine. So if you want to use the iuring command engine, so you will have to specify the iuring command as the engine. It will also take a command type option, which essentially means what is the type of uring command that we want to use, and we want to use the NVMe uring command. So we'll specify this option as NVMe. And in the file name option, you will have to pass the NVMe generate device. That's it. And you can run the workload using this engine. However, if you want to use the XMEI engine, then you can do that as well. For that case, you will have to specify the engine as XMME, and you will have to specify the XMME async option as iuring command. And with that, you can run any workload using this engine on this new path. Now, coming to performance, so I think there are two main aspects. We move from the ioctl passthrough to uring passthrough because we know that the ioctl won't scale as it is a blocking call. However, because iuring is a non-blocking call, so it will scale with the increasing depth. So we want to see whether we scale or not. So if you see this graph, the yellow line represents the ioctl pass-through and the green line represents the uring pass-through. So if you see the ioctl pass-through doesn't scale because it's a blocking call, whereas uring pass-through, because it's a non-blocking call, it will scale as the depth increases. The second aspect is how is the performance of this new path compared to the existing block IO path. The performance of the existing block IO path is represented by this line in gray. So if we see, the uring pass-through is as good as the regular iuring, which is again a good thing about this path. So now with this, I would like to conclude this session. Thank you.